All right, now let me try to go a little bit faster doing the same things. It says here in example 2a, determine whether the function f of x equals 1 over x minus 1 is continuous at x equals 1. Justify using continuity tests. Again, I'm going to look first at the picture. And as I can see, this does have, it's discontinuous, the function overall. It's discontinuous at this point here. X equals 1 is what it appears to me here. Let me draw the line, make sure. At the value x equals 1, yeah, we have a break here. So it is discontinuous, and this is infinite discontinuity. So we have infinite discontinuity at x equals 1. And now a way of testing that is when we plug in x equals 1 to the equation, we should run into problems. Sorry, let me fix that I. So here's your test. Let's look back up the equation here. If we said f of 1, that means we plug in 1 to the equation. I'm going to plug in 1 where I see the x. So I'd have a 1 come in right there in that equation. Well, as I go to simplify here, I have 1 over 0. And in math, you're never allowed to divide by 0. And that's why we have an asymptote. It's actually undefined. That's why we get an asymptote. So this is a way of proving that the limit does not exist. So the way you would write that is limit. This means, remember, what happens to y as x approaches 1 is the limit does not exist. All right? And that's why it's an infinite discontinuity. Let's try another one. This time, same type of problem, but on example B here, we have a different equation. So we want to know if it exists at x equals 2. Let's look at the graph here. On the graph, at x equals 2, it appears to be continuous. There's x equals 2, and it appears to be continuous. So we're going to think for a little bit. It appears to be continuous, but however, we need to test this. So the way to test, again, is you plug in the equation. Now, is this, yeah, f of, this time we want to find 2, and our equation is x minus 2. So I'm going to put in 2 minus 2 all over 2 squared minus 4. Well, as I go to simplify, I see I have 0 divided by 4 minus 4, which is 0. And again, I got problems here. All right, I'm just going to do problems. So here's what we need to do. Pre-cal, you'll find out that a lot of times we need to simplify the equations first. So I'm actually going to factor the bottom. Now that is a perfect square, which means I have an a term that's squared and a c term here that's squared. I'm subtracting. I could actually factor this if I wanted to. Draw an x. I'm going to factor the bottom. And a times c here is negative 4. It does not have a b, so it's 0. What are factors of negative 4 that add to 0? Well, 2 and negative 2. My a is 1, so that means my equation here, I'm going to rewrite it, is the same thing as x minus 2 over x plus 2 and x minus 2. Well, a little math here, and I can discover I could cancel these two factors, which leaves me with nothing on top. So you don't put a 0, you actually put a 1 over x plus 2. So now let's try this equation again. If I plug in f of 2, I discover that I'm going to get the value of 1 over 2 plus 2, which is going to equal 1/4. And so it looks like it exists this way, but it doesn't exist this way. This is what's called removable discontinuity. The truth is, this should have a little bitty hole right there because I had to remove something from the equation to make it work. Once I removed it by canceling, yes, it did work. But truthfully, in the very beginning, we had problems. So we knew it was discontinuous from this step, but this tells me it's removable because you can remove it and then have the equation work perfectly for you. So this is removable discontinuity.